Continuing on in chapter 6, which we have already started. And the primary thing that we talked about to start this chapter was clarifying the concept of endothermic versus exothermic. Okay? And we're going to do a little bit of review with that, along with one other main topic for today. And the first thing that I want to call your attention to is learning a new vocabulary word. The word enthalpy is a word you're going to see a lot in the next couple of weeks. It is simply a fancy word for the word heat. They're synonyms. Enthalpy. And we have seen this symbol before. This is the variable for enthalpy. What does delta mean? A change. A change in energy. A change in heat. And we're going to be looking at different ways to measure a change in heat for a reaction. And we're probably not going to get into this too much today, but one way to calculate it, and I'm sorry this got cut off down here. Okay. One way to find delta H is by knowing what the heat of the products is. Heat of the products minus heat of your reactants. And if you remember, we talked about this just a little bit when we started this chapter, when we were looking at energy curves like this, where your reactants are on the left, products are on the right, and your heat and energy, your enthalpy, is on the y-axis here. And let's just, put some numbers on this. Let's just make some up. Let's say the heat of the products, 4, heat of the reactants, 1. Heat of the products, 4 minus 1 gives you a positive number. What does a positive delta H mean? Endothermic. Okay? A negative delta H means exothermic. Okay, so endothermic comes from a graph that looks primarily like an uphill curve, like that one, whereas exothermic would look something like that kind of a shape. Again, you look at the y-axis, the heat of the products minus the heat of the reactants, you would get a negative answer. So sometimes delta H can be taken from a graph. Next week we will look at where you're given values not from a graph to plug in here. And today we're going to focus on a third way to find the heat of a reaction. And one of the things I want you guys to understand about enthalpy is that it is an extensive property. Now, before we refresh our memories about what extensive means, what does intensive mean? I think that one's a little bit easier to explain. Do you remember what intensive means? Yeah, Cole.
Isn't that something that doesn't change based on the amount of something?
Exactly correct. It's some kind of a property that doesn't change whether you have a little bit of something or a lot. Give me an example of an intensive property. James. Density. What's another one? Malleability. Melting point. Color. Things like that. I mean, if I have an ice cube versus an iceberg, same substance, very different amounts, they will have the same density. They'll have the same melting point. Okay? Enthalpy is an example of something that does change when you change the amount. What's another extensive property? Mass, what else? Volume, weight, okay? And guys, the easiest way to understand enthalpy being extensive, let me give you a very simple example. Let's say you have a lit candle, okay? Just a regular candle. You've lit it. If you put your hand over the flame, and I don't mean like right over it, so you're like burning your hand, but you know, if you put your hand above that candle, will you feel some warmth? Yeah, not much, but some. Would you feel more warmth if you were standing next to a gigantic bonfire? Yes, okay? A candle has a small amount of material. A bonfire has a big amount of material. Very different amounts of heat being released. Okay? And mathematically, it's a direct relationship. If I have a reaction like this, and the heat change associated is 252.8, and by the way, that being positive means this is an endothermic reaction. If I double the molar amount of what's, of the pieces in this reaction, the heat change will also double. It's a direct relationship. Question? No? Okay. All right. Now, this is our big topic for today, and it's not going to take us very long. Calorimetry basically means measuring the heat of some reaction in a laboratory setting. Okay? So we're doing calorimetry. We're going to do some calculations with it, but before we do calculations with it, I want you to be able to understand it conceptually, because that makes the math a lot easier. In calorimetry, you use a calorimeter. And if you just kind of look at these pictures, you can probably tell that one calorimeter is much more sophisticated than the other. Alright? This one is exactly what it looks like. And this is not my name for it. Okay, this is what it's called, a coffee cup calorimeter. Because it's typically a cup made of styrofoam. Can you tell me why it is that a lot of disposable, coffee cups are made of styrofoam? Why styrofoam? Yeah, go ahead. Okay. They conserve their heat very well. It means that material is a very good insulator. Correct. You can be holding a very, very hot cup of coffee, but you're probably not feeling that much heat from your hand because the styrofoam is a material that does not allow much passage of heat through it. So it makes an excellent calorimeter because it doesn't allow heat to escape or come in. So we will be doing a lab with this type of calorimeter. I do not have on hand a bomb calorimeter. Okay? I have no idea why it's called a bomb calorimeter because there's really no bomb involved here. Okay, but I mean, if you're going to name something, you might as well name it something cool. Let me explain to you what's going on here. All right? A bomb calorimeter is two chambers, one inside the other. This interior chamber is usually made of some metal, or is made of metal, usually steel. And whatever the reaction is, that's where that's happening. The chemical reaction will be taking place inside that internal space. Okay? The exterior chamber is usually made of something like concrete. Okay? And in between those two chambers is flowing water. Okay? Not just water that's sitting still. There's a little fan here that keeps that water moving. Okay? And this setup is a little bit easier to understand if you put this in context of like a nuclear reactor. This is a very similar setup to how a cooling tower works in a nuclear power plant. Okay? I don't know if any of you have ever seen a nuclear power plant, but do you know what I mean when I say they have those sort of iconic, like gigantic cement cooling towers? They look kind of like that. Do you know what I'm talking about? Anybody watch The Simpsons?
Yeah.
Yeah, okay. What's going on in those cooling towers is you have an interior chamber where a reaction is going on. Now, in a nuclear power plant, it's not a chemical reaction, it's actually a nuclear reaction. And guys, whether it's a nuclear reaction or we're just talking about calorimetry here, these are usually used in circumstances where that reaction is really, 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 really exothermic. What does that mean?
Lots of heat.
It releases a ton of heat, okay? And in those cooling towers, you've got water flowing around that chamber constantly, because if you didn't, the temperature gets too high and it gets out of control. And that's how nuclear meltdowns occur. All right? If for some reason the water stopped flowing or the water source was cut off and the water was no longer in there at all, the temperature would get too high and it could sometimes melt that interior chamber. And that would be bad. Okay? Now, they do have fail-safes in order so that, if should that happen, nuclear waste is not like leaching into the groundwater, but, it's a potential issue. But we're not going to talk about nuclear reactions. I just wanted, just for your information, just to explain to you that this is a very similar setup to the way that a nuclear reactor is working. And tell me this, guys, if this reaction, let's go back to a chemical reaction, if this is extremely exothermic, what do you think's happening to the temperature of the water if you just let it sit there over time? It's going to heat up. Okay? Probably not to boiling, but it will heat up. All right? And looking at how that temperature changes, like how high does it get, gives us an indication of how much heat is being released. Okay? And before we jump into the math with this, I need to refresh your memory on some terms here. And I want us to focus first on this one in the middle, because this is the one you should be familiar with, the one in the middle. Specific heat capacity. And that is a lowercase c, right? By definition, specific heat capacity is the amount of heat measured in, do you know what unit that's for? Joules, yep. The amount of heat in joules required to raise the temperature of 1 gram of something by 1 degree Celsius. Okay, let me give you an example. It is easier, let's say, let me back up. Let's say I have 1 gram of water and 1 gram of solid iron. Okay? Same amounts. 1 gram of water, 1 gram of iron. I'm going to tell you that it is easier to raise the temperature of the iron than the water. Let me say that again. It's easier to raise the temperature of iron than water. So would iron have a lower or higher specific heat capacity? Lower. Less energy is required to make the same temperature change. Okay? It has to do with heat retention as well. If you had 2 buckets, one with water and one with iron, and you had the exact same amount, and you had both of them at a very high temperature, the iron would cool down faster than the water. Now, let's look at this top one. Okay, what's the difference? Look at the units. Yeah, there's no unit of mass in this one. Let me refresh your memory about where we would use these. See if this equation looks familiar to you. Does that look familiar to you? It should. You all used it. Okay? Let's just review. Do you remember what Q represents? Heat. Okay? What's M? Mass. C is specific heat capacity. What's delta T? Change in temperature. Okay? That's where you would use this one. Well, look at the units for this one. This is not specific heat capacity. This is just heat capacity. No units of mass. So this is a situation where you could do this. Capital C, and that's a subscript P, by the way, but don't worry about that. No M. Doesn't need to be. There's no unit of mass to even worry about. Okay. What about down here at the bottom? What's the difference? Except for what difference? Yeah, instead of a mass, you could use moles. Right? It would be Q equals, yeah, N for number of moles times this, but you're never going to use this one in an equation. You could, but they just don't do that. Okay? Now, let me set up some scenarios where you're going to use these. Okay? Imagine, if you will, I ask you this question. You know, don't write it down, just listen. What if I asked you, how much heat is required to heat a swimming pool filled with water from 20 degrees to 25 degrees? And let's say I gave you the mass of the swimming pool water. You've got the mass, you have two temperatures. Do you remember, because you had to memorize it, do you remember the specific heat capacity for water? Please re-memorize that number. It is not given to you on your equation sheet. Okay? So let me say the question again, and you tell me what you would do. Let's say the swimming pool has 35,000 kilograms of water in it. How much heat is required to heat it from 20 degrees to 25? What are you going to do?
You have to change the mass to grams.
I have to change the mass from kilograms to grams. And then what?
Then you multiply the mass by C and divide by 5.
Yeah. Just plug in the numbers. That's it. Let me give you another example. Another situation. Just think about it. Imagine that I have a lead pipe in my hand. I don't know why I would, but let's just imagine. Okay? Right. And I'm holding it in the Bunsen burner. I'm wearing a glove. Okay. And goggles, of course. Alright, I take this very, very, very hot piece of metal and I put it into a beaker with room temperature water. Okay, you got it. Tell me, in which part of this scenario, the pipe or the water, which one will be losing or releasing heat? The pipe. Which means the water must be doing what? Absorbing it. Okay? Which piece of this scenario would have its temperature decreasing? The pipe. And the water's temperature would be? Okay. So the pipe's temperature is decreasing, the water's temperature is increasing. When does this process stop? When they reach equilibrium, be more specific temperature-wise. When they reach the same temperature. Well, ladies and gentlemen, all of what I have just said is just a roundabout way to say that when you have two pieces of material at different temperatures and you put them in contact with one another, one of them will be releasing energy, one of them will be absorbing, and ladies and gentlemen, those values are equal. If the lead pipe releases 100 joules of energy as it's cooling down, the water absorbs those 100 joules of energy. Okay? So, what would this look like mathematically? No, not a nightmare. This would basically be two MC delta T's equal to each other. One for the pipe, and one for the water. Now there's one little catch here. Which one of these is experiencing an exothermic process? Which one was releasing heat? The pipe. What kind of heats do exothermic processes have? Negative or positive? Negative. This one's heat will be negative. This one's heat will be positive. How do you make -5 equal +5? Put a negative on one of the sides. It doesn't matter which side. So, ladies and gentlemen, let me rephrase this a little bit. The energy released by the hot part of the scenario, energy released will be equal but opposite in sign to the energy absorbed by the cooler thing. Okay? Now, one last thing before I want you to try some of this on your own. One thing that's important, if we're going to use this logic, your delta T, your change in temperature, exactly, must be final minus initial. What if that gives you a negative number? That's okay. Okay? So, I would like for you to try these. I want you to pause wherever you are. I want you to notice a few things. First of all, this specific heat capacity has units of grams in it, so I can't leave that in kilograms. Alright, it also has degrees Celsius, and I was given Kelvin. How do you change a Kelvin temperature back to Celsius? Okay, subtract 273. Did some of you notice that the difference between two Kelvin temperatures is the exact same number as between those same in Celsius? Okay? So, if you went ahead and converted these to Celsius, fine. If you didn't, you'll still get the same answer. Now, do you have to put your answer in kilojoules? No. I rounded to two significant figures, but you could have kept it in joules. You could have left your answer as like 2.9 times 10 to the 6 joules. I just like kilojoules better, but it's totally your preference. Try the second one. Listen, you have some options. Okay, you have one other option in a problem like this. I want to call your attention to the fact that your textbook, and thus the solution manual, does not use that negative. They just say MC delta T equals MC delta T. Now, how can they do that? Because they do not have as a hard and fast rule that delta T is final minus initial. The way that your textbook does it is they always have delta T as the absolute value difference between the two temperatures. If you prefer that way, then you can ignore that negative. The reason I don't like that so much is because I like the fact that depending on whether delta T is negative or positive, tells me whether this reaction is releasing or absorbing heat. But again, mathematically, you really don't have to have that negative as long as you do absolute value here. Okay? I personally like this way better, and I personally think it gives you a more thorough understanding of what's happening, but it's ultimately your choice. Okay, now, ladies and gentlemen, number 1 was a very Chem 1 kind of problem.
Oh, no.
Number 2 was a Chem 1 honors kind of question.
Oh, no. Oh, God.
Can you see what's coming?
No, no.
Oh, it's really not that bad.
No.
Don't do it! Don't!
For the love of God. Don't look at it.
I always get the Chem 1 honors ones and I feel so good. Like, that's a Chem
People,
1.
it's really not that hard. I'm making it sound a lot worse than it really is. Okay?
That's a lot of words.
Yes, it is a lot of words.
Why are these problems so wordy?
Here is what I suggest. Because, listen, in these 2 chapters in particular, the word problems can be particularly wordy. My suggestion is to draw a picture, or if you're not a visual person, at least try to, before you write anything down, before you write any numbers down, before you do any math at all, try to visualize what is happening. Try to identify, is something losing heat? Is something gaining heat? Because there are a lot of numbers. I mean, this is actually a relatively short-ish kind of problem. All right? It's sometimes hard to figure out what numbers go with what. All right? So for this one, I'm going to draw a picture because it helps me. Let's read it. We have a sample of a compound called phenol. It is being burned in a bomb calorimeter. Stop right there. I'm going to draw a picture. A bomb calorimeter has an outer chamber and an inner chamber. Where does the chemical reaction take place? Okay. So let's put that phenol in there. C6. Okay. What's in this space between the 2 chambers? Water. All right. Let's keep reading. The bomb calorimeter, and I'm given some information about it. We're given a heat capacity. The temperature of the calorimeter plus its contents, that means including the water, increases from 21 degrees to 26 degrees. Let me make that a little clearer. The water is heating up. So where is that heat coming from that's heating it up? Okay, I'm going to draw an arrow. Heat is being released, which means, thank you, that this is an exothermic reaction. Okay? Now, last class, somebody asked an excellent question. Contents. What's included in that? Does that mean the phenol is also included? No, it doesn't. Do you remember we had that whole discussion about what's the system and what's the surroundings? Okay? This is the system. The box that it's in, the water, the calorimeter is considered part of the surroundings. Okay? So when it says the temperature of the calorimeter plus its contents, it doesn't mean the temperature of that reaction. It means the temperature of the water, essentially. What is the heat of combustion per gram of phenol? Okay, well, let me ask you this question. Hold on. In this scenario, do I have one thing releasing heat and one thing absorbing heat? Do I have two components in this situation?
Yes.
Yes, I do. Okay, your question.
Will you ever have endothermic reactions in bomb chlorine?
Typically, no, but you could. The way you would know that would be that the water would be cooling down. Okay, but the process we're going to do would be the exact same. So, oopsie. If I've got two components to a system, I'm going to set them equal but opposite in sign. The heat from the phenol reaction will be equal but opposite in sign, I'll call it Q-cal, to what's happening to the calorimeter. The phenol reaction is releasing heat, the calorimeter and the water are absorbing it. Okay, well guys, when the question says what is the heat of combustion, they're asking me to solve for this. This is my unknown. How much heat in this combustion reaction is being released? So if this is my unknown, that must mean I can find everything for the right-hand side. Let's look at what information we're given about this guy. What can I get from the temperatures that are given here? Okay, I can get a delta T. Am I given, like, the mass of the calorimeter or mass of the water? No. Okay, this is the only other piece of information I have about the calorimeter. Look at its units. Okay? What don't you see? I see kilojoules. I don't see grams. Which means I don't need the mass. Now, if you're still confused as to what we're going to do here, tell me this. Q represents what? Heat. What do we measure heat in? Joules or kilojoules. If this is what I'm given, something in kilojoules per degree Celsius, what could I do to this number to end up with just kilojoules? Multiply by something in Celsius. What in Celsius? Ding, ding, ding. This is a situation where we're going to do heat capacity times delta T. I don't need a mass. There are no units of grams to get rid of. So here we go. Bless you. What are the units for this answer here? Kilojoules. Just kilojoules. Now that's not the final answer here. Yes, Chris? I don't. Everything on this side is just for the calorimeter. Okay? Now folks, read what's written here. What is the heat of combustion per? What does the word per mean mathematically? Over or divided by grams of phenol. Well, here we go. Divided by, oops, not negative, grams of phenol. Now, guys, our final answer here came out to be negative. Should it be negative? Why? Because it was an exothermic reaction. I knew that before we did any number crunching. We knew that because the water was heating up. Okay? So that answers this one. What about the heat in units of kilojoules per mole? What do I do? Okay, convert grams of phenol to moles. Let's do that first. Molar mass off the periodic table. Then what? Which number do I divide? Okay, this one. That wasn't too hard, was it? It's the conceptual part that's hard. It's figuring out which number goes where is the hard part. That is where I'm going to stop.